Black holes as persistent field configurations. Holographic encoding in a Cartesian two-dimensional framework. In a strictly Cartesian space, a two-dimensional holographic projection does not encode a higher dimensional bulk in the conventional ADS-CEFT sense. Instead, it serves as a structured reduction of information, where the essential physical properties of a system are encoded on a lower dimensional surface. This approach provides a new perspective. Rather than interpreting black holes as isolated four-dimensional gravitational objects, they emerge as lower-dimensional quantum geometric entities embedded within our observable three-dimensional Cartesian framework. In traditional holographic dualities, such as ADS-CFT, a higher dimensional bulk is encoded on a lower dimensional boundary. Here, however, the Cartesian two-dimensional holography we propose does not invoke an independent bulk with its own gravitational degrees of freedom. Instead, it implies that the mass-energy interactions in quantum states traditionally attributed to a four-dimensional object are more accurately represented by a two-dimensional projection. This projection acts as an information screen, capturing the system's dynamic properties in a manner that is directly accessible within our three-dimensional space. This clarifying view suggests that what we mathematically model as four-dimensional gravitational phenomena may actually be manifestations of lower-dimensional field interactions. The encoding in two dimensions is not merely a reduction, but a reorganization of the information, allowing for a more natural and persistent description of black hole dynamics. Within this re-envisaged framework, black holes cease to be points of infinite density, a fundamental singularity, and instead appear as persistent, non-singular field configurations. The Dirac-Cartan Einstein structure supports this view by combining Dirac's insights on spinor fields, Cartan's introduction of torsion into the geometric fabric, and Einstein's description of gravitation. This synthesis yields a model in which mass-energy interactions do not collapse into undefined singular points, but are instead encoded as dynamic quantum geometric structures. In this picture, the event horizon is not a sharp, absolute boundary, but an emergent, structured interface that evolves in response to external influences. A compelling parallel to this lower dimensional encoding comes from the phenomenon of fine structure splitting in atomic systems, where energy levels split due to spin-orbit coupling. If similar spin interactions and geometric constraints operate at the black hole horizon, they may induce a dynamic splitting of the horizon into layered quantum states. This perspective implies that event horizons are emergent quantum structures, characterized by spin-orbit coupled substructures rather than a singular boundary. Fine structure splitting analogs could lead to horizon configurations that adapt and respond to perturbations much like excitonic systems in condensed matter physics. The quantum geometric tensor, or QGT, offers a robust framework for describing how quantum states evolve under external perturbations. In this context, the QGT could capture the response of black hole states to energy fluctuations akin to the fine structure splitting observed in atomic systems. Spin-torsion interactions, where the interplay between torsion from Cartan's theories and spin effects leads to a dynamic and adaptive horizon. Quantitative measures of how these non-singular encoded configurations evolve, reinforcing the concept of a continuously persistent black hole state rather than an abrupt gravitational collapse. Drawing analogies with excitons, bound states observed in semiconductor physics, this framework suggests that black hole horizons might exhibit discrete energy level shifts. These excitonic-like states would reflect the underlying quantum geometric structure, offering a model where the horizon is not an impenetrable barrier but a layered, dynamically coupled system. A bridge between gravitational physics and quantum field theory, where techniques from condensed matter could shed light on horizon dynamics. Looking forward, exploring quasi-one-dimensional phenomena and emergent string-like excitations in lower-dimensional gravitational interactions may further illuminate the fundamental nature of black hole encodings. Reframing black holes as persistent field configurations through holographic encoding in a Cartesian two-dimensional framework offers a transformative perspective. This approach shifts the narrative away from singularities toward a view where black holes are non-singular, dynamically encoded entities. By integrating the insights of Dirac, Cartan, and Einstein, and drawing on analogies from fine structure splitting and excitonic systems, this model not only addresses long-standing issues with singularities, but also opens new avenues for understanding the quantum geometry underlying gravitational phenomena.